Morning, everyone. In this video, I'm going to revisit the chain rule. There seems to be some confusion on how to begin a problem, especially when the chain rule is involved. So what I'd like to do is start maybe in a logical way, see when we do use it, when we don't use it, and then when we use it, how to identify the beginning point, right? So let's see how we do this. Right, so how do we look at the problem and see which way or how to begin it? So let's go ahead and look at some simple cases. Okay, remember what we have, okay? We have, let me see here, right here. These are sort of like the vanilla derivatives, just a straight derivative. Everything is a function of x by itself. And everything has an x in it, not any other function of x, just simply x. Here, when we introduced the chain rule, we said, okay, this represents some function of x. And if we look closely at it, we see there are two types of derivatives. One that involves a power rule. This is the generalized power rule, okay? And then the rest are extremely obvious. Either a sine or a cosine or a tangent, they're distinct. There's no confusion. In other words, if you see a secant, you will not go to the table and take the derivative using the sine. You'll do it using the secant. Same thing here. If we have an exponential with a base e, it's done one way. With a base a, it's done another way. There's an extra ln of a right in front. If it's the ln, the natural log of a function, it's very simple. It's the derivative of the argument over the argument. Sometimes this is written as u prime over u. If it's a log of a different base, it's 1 over the natural log of that base times u prime over u. So it's 1 over ln a, put it like this, u prime over u. They're distinct. But sometimes when we combine them, that's where confusion starts, okay? And by the way, again, here, y is a function of x. So when I say y prime, I'm basically writing a shorthand notation for dy dx. So let's look at this case. So here I want to put x squared prime, okay? Let's make it a little bit more interesting because let's pay 3/2. Again, I look at my table and I just have an x to a power with 1 in front of it. There's that little c right here. Just a simple power rule with x in it. So this one will be 3/2 x, and then 1 less that power, which will give me negative, just 1/2. 3/2 minus 1 is 1/2. Okay? Now, what if I have this? And I'm taking the derivative of that. Hmm? This is no longer an x to a power. So I cannot use this anymore. Okay? It's no longer an x to a power. Now it's some kind of a function of x to a power. So I have to use the generalized power rule, which says, again, use the regular power rule on this thing. Okay, let's make this a different color. Use the generalized power rule on this thing, and then take the derivative of that thing. So we'll do, basically drop the power 3/2, that thing to 1 less power. Again, I don't care what that thing is. Will not really matter. First, we apply the formula. So we see something to a power. That's not x. That something is not x. Something to a power. The generalized power rule says drop the power in front. That thing to 1 less power. So it will be 3/2 minus 1 is 1/2 times the derivative of that thing. Again, it doesn't matter what it is. So now let's put them in. What was in the circle here? It was x squared plus 1. And here, x squared plus 1 prime. You see? I am not concerned on what's inside it at this point. At this point, I am applying the definition of the derivative using the chain rule. Now I can start getting concerned of what's here. This one, we just write it the way it is. Now I take the derivative of this. Now I'm concerned of what's inside. This is a polynomial, so its derivative is the derivative of every term. So it will be 2x plus 0. And now we simplify things. This 2x plus 0 is 2x. This 2 and this 2 cancel out. So we get 3x x squared plus 1 to the 1/2. There it is. Okay. Now, let's go to a trig function. So sine x, and let's put a 3 here. Sine x prime. The derivative for this is, again, the 3 comes along for the ride. And here's the sine x right here. It's just sine with x as its argument. It's going to be the cosine of x. That is all. Now, what if I have 3 sine x squared plus 1 derivative? Again, when I look at this, I say, okay, I have a 3. The 3 is going to come along for the ride because it multiplies the function. I have sine of something. Again, let's put that something in a circle or a square. Doesn't matter. Have the sine of something. Sine of something. It's just a regular derivative of the sine, which is the cosine, times the derivative of that something. So that will be cosine of that something times the derivative of that something. Now plug them in. That something is x squared plus 1. Now I have to worry about this. 3 cosine x squared plus 1. Derivative of x squared plus 1 is just 2x plus 0. 2x plus 0 is 2x. Bring it to the front. Here's 6x cosine x squared plus 1. So that is good. Okay. Now, again, this is probably the simplest comparison between regular derivative without the chain rule and then the chain rule. And now we can extend it a little bit more. So now what if I have this instead? What if I have this? The derivative of 3 sine x squared prime. It's similar to this. The argument of the sine is just x, but this is where people start getting confused. And that's what I'm getting some feedback on. How do we begin this? At this point, we see there's a sign in there, but I'm really not really concerned whether it's a sign or something else. First thing we should see or realize, we have a power. We have 3 times something to a power. And I use the word something a lot because I really, at this point, do not care what that something is. It's not X. That's the main thing that I know. It's something else to a power. Okay. At this point, my mind should switch and say, power rule. Apply the power rule, irrespective of what is being raised to that power. So that's what my mind tells me. I'm going to do it. So let's do it. Power rule says we're going to carry the 3. We're going to drop the 2. That's something to 1 less power, then times the derivative of that something. Let's put it. See, I didn't care what was inside. I just followed the rule. Now, whenever I get to this point, now I'm concerned about what's going on over here. So this is 6 sine x times the derivative of the sine of x, which is just the cosine of x. And now I have 6 sine x cosine x. You can simplify them using a trig identity, but this is good. Okay. So again, whenever you see something like this, do not worry about the sign and start wondering, oh, gee, take the derivative of a sine. That's later. Right now, you should be able to recognize this is something to a power. Power rule precedes everything. Then you worry what to do with the rest. Let's take another one. I have room some here. Yep. Let's take, maybe E. Let's not take E. Let's just take tangent 3x squared minus 5. And the tangent is squared. I'm taking its derivative. So again, looking at this, I should not see the tangent. I should not worry about the tangent. I should say to myself, again, I have something right here to a power rule, which says drop the power, take that something to 1 less power, so 2 minus 1, times the derivative of that something. Okay. So we have a 2. 2 minus 1 here will give me a 1. So it's just a tangent 3x squared minus 5 times the derivative of a tangent of something. Again, I do not care what that something is. I see a tangent by itself to power 1. I see tangent to power 1 of something. Its derivative, according to this rule, is the secant squared of that something times the derivative of that something. Okay? So that's secant squared of that something times the derivative of that something. So I still have one derivative to take, so I'll rewrite the equation. Now the derivative of 3x squared minus 5, that's going to give me just a 6x minus 0, or 6x. Bring the 6x in the front, so that's 12x times tangent 3x squared minus 5 times secant squared 3x squared minus 5. There it is. Okay. So let's look at another one. Now let's just say I have this ln squared. The power is on the ln times e to the sine squared of x plus 1. I know we went from regular to now something that looks nasty. And I want to take the derivative of this. So d dx of this, the derivative. Or we could have put a prime over here, same thing. Okay? So let's see how we approach this. Again, the way we look at this is we need to work from the top level down. Okay? I do not have one thing to a power. First thing we go, is it a function to a power? It's not. Instead, it is made up of two things multiplied. Let me use a different color here. We'll call this F and G. I have two things multiplied. That's the first thing that should come to my mind. I don't care what F is. I don't care what G is. I care about two things multiplied. Take the derivative. And we have a rule for this. It's called the product rule. If I have two functions of x multiplied, f and g in this case, not three of them, two of them, the derivative of the product is the derivative of the first times the second plus the derivative of the second times the first. Well, let us just apply it blindly without even worrying about what f is and what g is. That's the first step. Let's just do it. And the more you practice, then later you can start playing with things and seeing shortcuts and simplifications. But right now, the derivative is f prime g, then plus g prime f. This is the definition. And let's write them down explicitly. Okay? So what is f? F is ln squared of this. So let's write what basically f prime is. So ln squared, 3x squared minus 1 prime. Again, I'm not concerned of what I'm taking the derivative of. It's f, something. I'm taking prime times g plus g prime. G is that ugly thing. Fine, write it. Says g prime, there is g prime, times f. By the way, sometimes people write tangent squared x, which is the same as tangent x squared. Ln squared x is ln of x squared. Okay? The square here is not on the x. The square here is not on the x. It's on the natural log. In other words, this is like tangent x times tangent x. Ln x times ln x. The other way will be tangent x squared. It's on the x. So this is the same as tangent x times x. Ln of x squared. This is ln of x times x. Okay? Two different things, depending what the square is. All right? So now that we've written according to the definition where things should go, now we apply. Now let's start getting concerned on what I'm taking the derivative of. Here I have a natural log of something, but the first thing that I see, I have something to a power. Again, ln squared x, something, is ln of something squared. I have something to a power. It happens to be the natural log, so what? But I have something to a power. Whenever that happens, automatically your mind should switch power rule. So power rule for the first one, the red, meaning drop the power. That's something, here it is, to one less power, so 2 minus 1 is 1, times the derivative of that something. Okay? Okay. Again, this looks like I had something squared. I'm sorry. Something squared prime. And this something here happened to be the ln of 3x squared minus 1. Power rule says drop the power. That's something to one less power times the derivative of that something. But if that something is the ln, here's the ln goes in here, and now I'm taking the derivative of the ln. Okay? And this is where I think some confusion will come, because you say, oh, okay, drop the power, ln of 3x squared minus 1. Now take the derivative of 3x squared minus 1. No, power rule, irrespective of what's being raised to that power. And I'm done with this, is partially, because now I still have this to worry about in the next statement. So I just put in the other one here, e to the sine squared x plus 1. Plus, now I have this here, the cyan and taking its derivative. What do I see? I see e to something. That's it. I don't care what that something is. Here it is. E to something itself times the derivative of the power. That's what we will do, not caring what the power is itself times the derivative of the power. That took care of the cyan. Then we go back to red and write. There it is. One step at a time. All right, we have a derivative right here we have to concern ourselves with, then a derivative right here. So let's take care of the red. Here's 2 ln 3x squared minus 1 times. I have the derivative of what's inside right there. I look at it and say, oh, it's a natural log to the first power. Okay, it's not a power rule now. It's just a natural log of something. So the derivative is the derivative of that something over that something. So the derivative of the argument over the argument. Okay. Then the exponential plus, now here we have the exponential times, I have the derivative of something right here. Let's look at that something closely now. It's some function of x raised to a power. Again, sine squared x, this is the same as sine x squared. Okay? So I have something to a power. It happens to be a sine, so what? It's something to a power. Drop the power. Again, just a regular power rule now. We're still in blue. 2. That's something to one less power times the derivative of that something. That something was the sine. So it's sine x plus 1 prime. Then ln squared of 3x squared minus 1. All right? All right, let's continue. Here I have 2 ln of 3x squared minus 1. Derivative of 3x squared minus 1 right here is just 6x. over the denominator times the exponential plus the exponential itself, which we can factor out. I'll factor out in just a second. Times 2 sine x plus 1 times. What's the derivative? Now here I have a derivative to take still. Oh, I see it's a sine of something, not something to a power. It's just a sine of something. Not sine squared, not sine cubed, not sine to the 3/2, just sine of something. Its derivative is the cosine of that thing times the derivative of that thing. Then I still have the red ln squared 3x squared minus 1. Maybe I should write smaller on the first part. So let's go here. This gives me factor out at e. Let's keep it blue. So e to the sine squared of x plus 1 times. Here I have 12x ln of 3x squared minus 1 over 3x squared minus 1. I factored this guy out, so now I have 2 sine. Now, what's the derivative of x plus 1 right here? Derivative of that is basically 1. So that will be 2 sine x plus 1 cosine x plus 1 ln squared of 3x squared minus 1. So I can still factor out an ln. So e to the sine squared of x plus 1 times the ln 3x squared minus 1 brackets. This goes out. So I have 12x over 3x squared minus 1. Here, 2 sine of something, cosine of something. That is the sine of 2x plus 1. And the ln of 3x squared minus 1, because I factored one of the ln's out. Now, unless I made a mistake, this is it. So again, yes, we're using the chain rule, but you need to basically practice on what you see first. Here I see a jungle. Natural log, squared, 3x minus 1, sine squared, x plus 1, exponential. But step a little bit back and say, okay, I have 2 things multiplied. That's what I start with. Okay? We chisel away at the problem one statement at a time, and in every statement we apply a rule. So first, the product rule. I have a function times another, 2 things. Derivative of first times the second plus derivative of second times the first. Now, if the first is ln squared of 3x squared minus 1, its derivative is that with a prime on there. Or some people would put ddx over here. That's fine. Either way. Don't take the derivative yet. Write it down so they can see it explicitly. Now, once you saw it explicitly, now you interrogate this. I'm seeing ln to a power. That means I have a function to a power. It happens to be the ln. So what? Here, it happens to be the sine. Big deal. Power rule. Drop the power. That's something, which is the ln to 1 less power, times the derivative of that something, which is the ln. There it is. And you continue the process all the way down, chiseling away one statement at a time, one rule at a time. And then at the end, if you can simplify and combine, that's great. If not, then you can't. That's fine. But at least you've done the derivatives one statement at a time. Again, consistent with the rules that we talked about before. And this is sort of like how you should start the problem, okay? By just looking at it from a 50-foot view, then come down a little bit, then come down a little bit until you basically get to something like this. Get to something like this up, and then work with this. Okay. I hope this video helped you at least get started with your chain rule derivatives. Please let us know if this helped, how it helped, and then if you have any questions or concerns, just drop us a note. I appreciate your time. Thank you, and we'll see you in the next video.